All right, so our next look is going to be at solving problems involving equilibrium, which is also called statics. When you have multiple things going on, right, you want to choose one object at a time, make free body diagrams for each object and all the forces acting on it. Choose a coordinate system, resolve forces into components. And again, as we did the problems before this from 9 to 1, we really want to choose a coordinate system wisely. Um, write equilibrium equations for the forces, and then choose any axis perpendicular to the plane of the forces and write the torque equilibrium equation. So this is a little different. A clever choice here can simplify the problem enormously, and we will look at different situations. Then, of course, solve. Um, so our previous technique may not fully solve all statics problems, but it's a good starting point. So we have this object on this table, right? We got two forces on these legs pushing upward to hold this table. We got the mass of our object and the table going down, but this object's not centered on the table, it's over to the side, so we have this going down this way. And you can see we have a lot of different things going on here with this CG being the center of gravity, okay? So we have to think about all these different things when we start to solve statics problems. If a force in your solution comes out negative, as FA will, it just means that it's in the opposite direction from the one you choose. And this is an easy fix, so don't worry about getting all the signs of the forces right before you start solving. The negatives and positives will work themselves out, okay? And as we do, again, as you do problems, you'll see this. And you can see with from the edge of the table to here, right, FB, and you got FA, you get your distances and so forth, okay? But a trivial fix. If there's a cable or coordinate problem, it can support forces only along its length. Forces perpendicular to that would cause it to bend. So as we look at this right here, right, there's our force of tension, all right? It will only support forces along its length. So you look at these different tension forces, right, in the hinge forces, they're along its length when we talk about hanging that sign, okay? And then, of course, we're going to apply it to some arms and joints because those are ones that we can talk about and you can actually try to do on your own by feeling it. So, for example, here's the force of the elbow joint. There's the center of gravity of your arm. There's the ball that you are lifting or the object that you're curling, right? There's the force in the muscle to lift that up, and you can see all the information's provided, and we just use torque to solve in statics. And you can see if we bend it at 45, and this is an example that we'll look at. The angle at which this man's back is bent, an enormous force in the disc at the base of the spine as the lever arm is so small. So you can see, and let's see if we can show this to you. So we're talking about the vertebrae, right? And you have the vertebrae, and you got the distances along which, right? And you can see the different weight, the weight of the head, then you got the weight of the arm, and then you got T, you got the weight here, right? And then you get and then you get weight of the total person, and it's all kinds of information that's provided, but it's all a percentage of the total weight of the person. So we can use some of this information to solve, and then of course you're looking at the force of the lever arm right here on your back, thanks to the discs at the spine. You can see the force is here, and we'll look at problems probably not this difficult, but just understand that this will be or could be things that in applications when we talk about the human body. So first one, balancing the seesaw, very typical problem, probably one that you should be able to do without issue. But a board of mass M serves the seesaw for two children, as shown in the diagram. Child A has a mass of 30 kilograms and sits 2.5 meters from the pivot point. His center of gravity is 2.5 meters from the pivot. Okay, that's what that means. At what distance x from the pivot must child B of mass 25 kilograms place herself to balance the seesaw? We're going to assume that everything's uniform and centered over the pivot. So this may be something you did as a kid where you get on the seesaw and you try to get it to balance, and you have to try to figure out, okay, this kid is heavier than this kid, so where does this kid have to be to make sure that everything gets balanced. And that's what we're going to figure out mathematically. Do it now.
All right, so we're on the seesaw. Kind of do some pre-drawing here. Here's our 30-kilogram kid, 2.5 meters away. Obviously, there's a force going down here, right? And that would just be the force of gravity on this kid, which would be 30 times 9.8. We have a downward force of gravity here, which would be equal to 25 times 9.8. We got the force of gravity on the board going down, and the goal is to get all these forces equal. Well, that equal force would have to be our normal force, which right now I don't know if we know it or not, right? So we know that everything's going to be here in the y, okay? There's no forces going this way. Everything's up or down. So that makes the problem a little bit easier. So I want to find my net force in the y. And that's the direction I want to take here. And I know it's going to be equal to 0 because we want everything to be balanced. I chose a positive torque to be this way, negative torque to be going in the other direction. I don't think that's going to make much of a difference here because when in the y, we're going to have up and down. But anyway, we established that. So I want to add up my forces. In the positive, I got normal force. In the negative, I got this weight, right? Which is going to be negative 30 times 9.8. I got the board, which is negative 4 times 9.8. And then I have this, which is negative 25 times 9.8. So, and that's all going to be equal to 0. So I can put all that together, and I should be able to find my normal force. So that's something I can do. I'm seeing if I have the numbers, if I have my answers written down here or not. And I don't think I do, so we're going to have to calculate, which isn't a big deal. So I got 30 times 9.8, f of n minus 294, 4 times 9.8 minus 39.2, then I got 25 times 9.8, 245. And so I'll combine like terms and get my normal force to be 294 plus 39.2 plus 245, and I get a normal force of 578.2, okay? So I've established my normal force in my balancing of the forces, okay? So I got a force equation and I've solved. Now I want to find a torque equation. For my net torque to be 0, I gotta pick a 0 point. So one, I'm going to pick my 0 point to be right here. All right. So I think I can get the screen here. Okay. So net torque has to be equal to 0. And to do that, I just find the torque of all my different objects. So I have my kid that I know the mass of, right? The 30 kilogram kid. And I know that my net torque for him, since he's going to go down, is going to be positive. So I'll have 30, actually his force of gravity is going to be 294 times his distance, which is 2.5. Then I'm going to pick the board, right? The board, and the board's going to be on my 0 point, okay? So the board's going to be on my 0 point. Since the board's on the 0 point, I just take the mass of the board, or the force on the board, which is this, times 0. So that would be plus 0. And then I want to put the torque on my unknown distance. And that force in that person we've already figured is 245 times x, which will be that distance, whatever we determine that to be. So now we can solve. Net torque is equal to 294 times 2.5. 735 minus 245x. Means I can solve that since my net torque is 0. It's 735 minus 245x. Bring everything over, solve for x. 735 divided by 245, x is 3 meters. So I know that to make this balance, that person has to be at 3 meters.
And then this is the example from the earlier. So we got a uniform beam of 1,500 kilograms, supports a printing press of 15,000 kilograms, all right? It's 5 meters from the right of the support column, so this is 5 meters from here. We want to find the force on each of these vertical support columns. Do it now.
All right, so I'm drawing those small shows you what's going on. So I got force A from this leg going up equal and opposite to the weight going down. Same thing with force B from this leg on the table. Center of gravity of my table is right here, 1,500 kilograms, so 1,500 G's the force. The force on the paper machine is 15,000 G. And then our distance is 10 meters from A to the center, 10 to B, with this paper machine being halfway distant between center of gravity and our post B. So the thing is that now we want to draw our two equations. So let's think about forces and what we're looking for here. The first thing is that everything's going to be on the y again, so that's good, right? I know all my forces are going to be on the y. So FA and FB, so my net force is FA plus FB, and then everything else is going down. So I got the force here minus 1,500 times 9.8 minus 15,000 times 9.8. So that's going to be my net force, and my net force is going to be equal to 0. All right, so there's my force, my forces that are being used here. And now I can draw a torque formula. So net torque is also equal to 0. But let's take a look, and we got to choose a 0 point. And so if I choose a 0 point that can eliminate A or B, I'm better off doing that. So I'm going to make my 0 point right here. Okay? And I'm going to make A and B become my positive forces here. And so when I look at this, my torque, I know the torque for force A times 0 will be 0. This force, right, the torque here will be 1,500 times 9.8 times the distance from our 0 point, so 10 meters. This is also going in the same direction, so I think we're going to make those negative, I said. So then this one going down will be negative, the torque here. And when I look at that one, it'll be 15,000, right? 15,000 G times the distance of 15. So 15,000 times 9.8 times 15 meters, because it's 10 plus 5. And then force B is going to be times 20 meters. And since my net torque is 0, this is going to be 0. So now I just plug and chug my calculator here. 1,500 times 9.8 times 10, negative 147,000 minus 15,000 times 9.8 times 15, 2205000 plus 20 FB. Combine like terms, solve for FB. You can do all of that yourself. But divide by 20, and my force on B is going to be 117,600 newtons. So I found my force of B. Then all I do is I take this and substitute it into here, right? And then I can solve for force A because my net force is equal to 0. So I'm going to bring this equation down here equal to 0, force A plus 117,600 minus 1,500 times 9.8 minus 15,000 times 9.8. I can now solve for FA. 1176 minus 14,700 minus 147,023. And FA should be 44,100. And that's just to pick up the slack. So we found both forces.
And then here's the other diagram of the hinged beam and cable. So we got a beam here, all right, that's 2.2 meters long with a mass of 25 kilograms. It's mounted by a small hinge on a wall that we see here. The beam is held in a horizontal position by a cable that makes an angle 30 degrees with the beam. And the beam also supports a sign that's 28 kilograms suspended from its end. So we want to find the components of force FH that the smooth hinge exerts on the beam and the tension in the cable. Lots going on. This will be a long problem, but you'll see how we can fit this all together. We talk about breaking things down into separate places. And also, you can see the initial setting of the axis here, right? Where the origin will be here and here for these two situations. Do it now.
All right, so there's my drawing, and you see what we got. We got all these different forces acting here. Here's the sign and the weight that the sign has. Here's the weight of the beam, okay, and they're both going straight down, so that's going to be in the negative y. So the first thing we want to do is we want to sum our forces into y. I got F hinge of y, the force in the hinge of y going up, and I got the force of tension of y going up. So those are the two forces pushing up, and those are the ones that are going to hold the weight of the negative 245 and the negative 274.4. So now what I have is a nice force equation for that. Now in the x, my forces in the x, I just have these two, and I'm going to make right positive, so FH of x minus F tension of x are going to be equal to my net force in the x. Okay? And all my net forces are 0, so FHY plus FTY, and I'm going to just do some math here to put this all together. 245 and 274.4 negative 492.4. Okay. Here, this is 0. And you can see what that means is that these two forces in the end are going to be equal to each other. Okay. So those two x forces are going to be equal. All right. So now we want to look at torque. Again, since we're standing still, our net torque is going to be 0. And as we look at this, we want the axis at the point where FT and mg act, or the sine act, sorry, they call it mg on the problem, is right there. So I'm going to make that my 0 point. And then I'm going to find the torque, right? And I want to get it so I only have one unknown in my torque, which I can. So let's solve for torque here. We know the length of our beam is 2.20 meters. We know that going this way, the force on a y is going to turn this this way, so that's going to be negative torque. So I have 0 is equal to negative FHY times the distance of 2.20 meters, all right? And then we look at the weight, it's gonna pull it in this direction, so that's gonna be positive torque. So that's gonna be plus 245 times the distance of 1.10. Now we can solve for FHY. So let's do that. I'm going to bring this over 245 times 1.1. So it's going to be negative 269.5 on that side of the 0 times negative FHY times 2.20. FHY, negative 269.5 divided 2.2. 122.5 newtons. So that's going to be our force here. All right. So now we found our y component of our hinge force. So now we can start to look at other things to solve. I can put this into here, right? And when I do that, I got 0 is equal to 122.5 plus ft of y minus 492.4. Solve for ft of y, 122.5 minus 492.4. ft of y is 369.9 newtons. So now I found the y component of my tension force. And then from there, I can start to find other things. So now that I know my y component, right, and I know my y component here, and I know the angle's 30 degrees here, I can work my way through and use tangent to find my ft of x. So the tangent of 30 is equal to opposite, which is ft of x over ft of y. I multiply both sides by that, I can find my ft of x. So ft of y is 369.9 times the tangent of 30, and ft of x will now equal 214 newtons. All right, so now I have 214 newtons for ft of x. And then once I know that, I can find this tension by just doing opposite over adjacent, or I can do Pythagorean Theorem actually. Ft of x, so I can say Ft of x plus Ft of y equals force of tension squared, right? And I know Ft of x is 214, Ft of y is 369.9. So now I can find my overall tension force. So 214 squared plus 369.9 squared. Take the square root of my answer, and I get a tension force of 427 newtons right here. So that's 427 Newton tension force on my for my F of T. And I think I'm good. I don't think I have to find anything else. Oh, we want to find the components of force so we got FH of y to be 122.5. So if that's 122.5, then all I have to do is substitute that into here, and I can also use Pythagorean Theorem, because I can find that. So I take my Ft of x, which is 214, and that is my Fh of x. If my Fy of x is 122.5, is 214, I can do the Pythagorean theorem to find that. So 122.5 squared plus 214 squared, take the square root of my answer. I get the force here of the hinge. It's 247 newtons. So I can solve for all that. Again, the big thing is this. Make y, make x, get your forces equal to 0 since everything's stationary, and then make a torque equation, and then start to solve for unknowns.
Ladder. So we got a 5-meter long ladder leaning against the wall at a point 4 meters above the cement floor. The ladder is uniform and has a mass of 12 kilograms. Assuming the wall has no friction, but the floor is not frictionless, so this will stay still. Determine the forces exerted on the ladder by the floor and by the wall. So we have this and we have this. Find those forces. Do it now.
All right. So here's what we got. We got a ladder leaning up with mg being the weight. We got a force on the cement going this way. Broke it down into x and y here. And then you got the force on the wall pushing back going this way, okay? And since we're in equilibrium, all things are the same, right? So we know that the force, some of the forces on x is 0, some of the forces on y is 0, and net torque is 0. So let's start with x. And on the x, the forces we got are W going this way in the wall, and we got x going this way. So we know that the force of cement in the x minus the force of the wall is going to equal 0, which means the force of cement in x is going to equal the force on the wall, all right? So let's take our forces in the y. They're also going to be equal to 0. If our forces in the y are equal to 0, let's look what we got in the y. All right, so we got going up, we got the cement force, and going down, we got the weight. And I think that's all I saw, yeah. So on the y, 0 is going to be equal to the force of cement in the y minus the weight of the ladder. Now the ladder has a mass of 12 kilograms. So 12 times 9.8. So Fc of y is going to be equal to 117.6 newtons. So we know the force in the y, okay, from the floor. So we got that. And now we want to do torque. And the torque equation, net torque is also equal to 0. And this is going to be a little more difficult because we have to think about all the different torques acting and the 0 point we want to choose. So what we're going to look at is the forces that are going to be causing this object to turn, right? We got to think about the weight of the ladder, and then we got to think about the center of gravity. Okay. We know the weight of the ladder. We know that, I'm sorry, not the weight of the ladder, the force in the wall, my fault. FW force in the wall. So we know where the force in the wall is located. So we know the torque there, all right? So I have that pushing this way. And so force here is at 4 meters. So I'm going to make my floor 0, okay? And then I'm going to look at the distance from the floor up, right? To get that distance for the center of gravity that's going to push against us, okay? So I look at mg, and I got to try to find xo, right? And so I got to think about things that I know. I know the ladder has a length of 5 meters. this distance that it is away. Because this is 4, this is 5. I can use Pythagorean Theorem. So my Pythagorean Theorem to find xo squared plus 4 squared equals 5 squared. So that's a 3, 4, 5 triangle. 3 meters. There. Which means, all right, which means if I look at the at this force, here's my 0 point, then this is going to be going 3 meters, or half of 3 meters. So it's going to be about 1.5 meters away. So it's going to be minus 1.5 times the weight of the ladder, which is 12 times 9.8, 117.6. So now I can solve for FW. 1.5 times 117.6 divided by 4. Force on the wall is 44.1 newtons. And now I can bring that over to here. If the force on the wall is 44.1, then my force of concrete on the ladder in the X is also 44.1 newtons. And then once I know that, I know my X and my Y, I can find this force of concrete. So force of concrete squared is going to be equal to 44.1 squared plus 117.6 squared. So force on concrete should be 44.1 squared plus 117.6 squared. Take the square root of my answer. I get 126 newtons. So the force on the concrete should be 126 newtons. Now, we can find the angle that the ladder needs to be. We know the two legs, so I would take the arctan of opposite over adjacent, so the arctan of y over x, or inverse tan. My y is 117.6 divided by 44.1, and my angle is going to be 69 degrees. So now I know the angle of the ladder also.
And then one of the biceps problems. How much force would much a bicep muscle exert when a 5 kilogram ball is held in hand with the arm in horizontal, okay? And B, when the arm is at a 45-degree angle. The biceps muscle is connected to the forearm by a tendon attached 5 centimeters from the elbow joint, so that's that distance here. Assume that the mass of the forearm and hand together is 2 kilograms, and their center of gravity is shown, which is 15 centimeters from the elbow. Do it now.
All right, so I made a really generic drawing here of all of our forces. You got the force in the joint, force in the muscle, center of gravity, and then you got the ball in the hand, right? And we know that it says the torques here is going to be 0. We're going to make the force on the joint our 0 point, okay? So we don't have to worry about that number, but now we got to look. So the distance from the force to the muscle is 5 centimeters. We got to convert that to meters. Since that's going up, we'll make that positive, just for giggles. So we got plus 0.05 times force on the muscle. Center of gravity is going down, so we'll make that negative. That is going to be 15 centimeters, so 0.15 meters, and it's going to be negative since it's going down, so minus 0.15 meters times the mass of the arm, what we say, 2 kilograms. The mass is 2 kilograms. Okay, yeah, 2 kilograms times 9.8. And then we got the ball, which is going to be a full 35 centimeters, so 0.35 meters times the mass of the ball, which is 5 kilograms times 9.8. So let's, net torque is going to be 0. So 0 0 is going to be equal to this, so let's go 0.05 force M. And then let's see what all our negative terms turn out to be. 0.15 times 2 times 9.8. And then we go 0.35 times 5 times 9.8. Together, those are negative 20.09. We move that over, divide by 0.05. I get a force of 400 on the muscle, 402 newtons. It's a pretty strong force on the muscle there. Okay. So let's talk about just raising it up. And the lever arm is reduced by a force factor of cosine 45 for all three forces. So our torque equation will look like the one just that we just did. All right. Except that each term will have its lever arm reduced by the same factor, which will cancel out. So what will happen is each of these forces here and here will be reduced by cosine 45, just like this one. But then in the end, when we solve, if we divide everything, get cosine 45 out of the system, we still have the same equation, which means the force is still going to be the same, 402 newtons.